matter elasticity in the last lecture. So let's continue ahead with that today. So we had understood the definition of stress and strain, and also the relationship of Hooke's law, that stress and strain's ratio is constant as long as the amount of stress is less than something called the elastic limit. So to that end, we were discussing about the longitudinal elasticity or tensile elasticity and Young's modulus from that. Okay, so in elasticity, towards the end of the last lecture, we were looking at the application of Hooke's law in the case of longitudinal stress and strain. So what we saw is that if you have a longitudinal kind of material, which you have either extended or you have compressed because of the action of external forces, then that creates a stress in the material in the form of a tensile force or an internal conservative force, which is restorative in nature, which is basically all about the property of elasticity, that the body has a tendency to retain its original shape because of the restorative nature of the internal tensile force. So it is the restorative force due to the material's elasticity. That is the property of elasticity. And we say that in this particular situation, here if the body has been extended or here if the body has been compressed, so for longitudinal deformity, that is extension or compression, we define the longitudinal the longitudinal strain as the fractional change in length. And we define the longitudinal stress as the tensile force per unit area of cross section. And Hooke's law basically tells us that the longitudinal stress divided by the longitudinal strains ratio is the material property called Young's modulus of elasticity. Which is the material property. Of course, this equation, this Hooke's law equation is valid, not indefinitely, but this is valid for the condition that the stress T by A is less than equal to what we call the elastic limit. Okay. So we had just started to look at numerical examples based on this, and we'll continue from that point onwards today. So you need not note down this point. You have seen this in the previous lecture. This is just a quick recap of the application we were looking at last time. So this part is just that much. Okay, let's look at example of application of this. So we have something like this now, where we have a combination of metallic thin wires as well as a combination of two blocks. So these are metallic blocks, rather metallic wires used to suspend two blocks. So wires 1 and 2 are light metallic cables, and A is a block of mass, say 50 kilograms, and B is a block of mass 25 kilograms. Now for wire 1, given to us that the Young's modulus of the material is 6 into 10 raised power 11 Newton per meter square. The natural length is 5 meters. And the cross-sectional area is 2 centimeters square, whereas for wire 2, the Young's modulus is 2 into 10 raised by 11 Newton per meter square. Natural length is 2 meters, but the area of cross section is 0.5 centimeters square. Don't go by a diagram where the wires look equally thin and all that. Okay, just assume this. So we have to find stress, that is the tensile stress in each wire. And we have to also find the elongation, delta L1, let's say, and delta L2 for both wires. Okay. So these lengths that are given to us, L1 and L2, they are the natural lengths.
So can you scroll up for a minute?
Yeah, I can, but that is the part that you've already seen in the last lecture. It's there in those notes. Okay. So
Okay.
basically, you have to use this formula over here. So I'll just copy down this formula for you. You can refer to this. So this is a direct application of Hooke's law. Now you have to just substitute the values according to the data given in the question, including the weights of the blocks. So we'll be applying this Hooke's law over here.
Okay, sir. Thank you.
So this is all you need from the above section. Right? Okay. Okay, so now just apply your general knowledge about mechanics, free body diagram of the blocks A and B, etc. to find out first of all the tension in each of the wires. From the tension, you will get the answer of the first part. Stress is nothing but tensile stress, or longitudinal stress is nothing but tension divided by area. And then you have to apply Hooke's law to get the second part. That is, you get the strain first, and from the strain, you will be able to find the extension of each of the wires. Right. So just try this out. Okay, Rakshit, I'm just scrolling up for some time. You can go through this, but as I said, like this is there in your previous lectures notes and all. Okay. This is what we had discussed, and also we had done a couple of questions of application of this. Let's work out this question now. So you can see that, let's say the tension in wire B is T2 and the tension in the first wire is T1. So from the free body diagram of block B, you can see that T2 will be equal to its weight. So T2 is equal to 250 newtons. So therefore longitudinal stress in the second wire will be T2 divided by E2. So that will be 250 newtons into divided by 0.5 into 10 raised power minus 4. So that will become 5 into 10 raised power 1 plus 6, 1 plus 5, right? So 10 raised power 6 newtons per meter square. So that is the longitudinal stress in the second wire. Now you look at the free body diagram of block A and you will understand that T1 is going to be T2 plus the weight of this block. So you see that T1 will become 250 plus 500 or 750 newtons. So accordingly, the longitudinal stress in the first wire will, according to the data of the question, be 750 newtons divided by 2 centimeters square. So it will become 3.75 into 10 raised power
6.
6 yes, Newton per meter square. Okay. So it's like very formula based, as you can see. You have to just make sure that your concepts of calculation of tension is correct from very basic principles of Newton's laws. Nothing very difficult at all. Okay. And once you got the stress, now the Newton's laws part is over. What you have to understand is application of Hooke's law. So this is the first part. You got the stress in each of them. Now apply Hooke's law so that you will get the strain. And the strain is the fractional change in length. You already know the natural length. So from fractional change, you will get the change in length delta L itself, which is the extension in each case. Okay, so now let's come to the second part. Just use the general formula that stress upon strain is equal to Young's modulus. So from this we can generate the formula that strain is equal to stress divided by Young's modulus. So ultimately the extension in length is equal to stress divided by Young's modulus into natural length. So we'll just apply for each of the wires. So for wire 1, this will be T1 by A1, which we already calculated. Just have to plug in the value of Young's modulus and natural length. Okay. So 3.75 into 10 raised by 6 divided by the Young's modulus, which I think was 6, right, into 10 raised by 11. Yeah. And the natural length was 5 meters. So 3.75 into 5 by 6 into 10 raised by minus 5 in meters. So that is 5 by 6 into 3.75. Very small amount of extension you can see.
So 3.125 into 10 raised to minus 5.
Okay. So we can even write that as 31.25 micrometers. Because this will be, as you said, 3.125 into 10 raised by minus 5 meters. So you can express it in micrometers. Okay. So this is the amount of extension. And similarly, we can do the calculation for the second one. So 50 microns or 50 micrometers change.
Sir,
Yes.
sir, why you have multiplied it by 2?
2 meters is the natural length, beta. L2.
Okay, sir.
Understood now? If you wanted to just find the strain, then it is just stress upon Young's modulus. But यहाँ पे मुझे क्या निकालना है? Change in length है ना? So further it is strain into natural length. Got it now?
Okay, sir.
Okay, now moving on. Another property of a body under stress or strain is that it stores what we call elastic potential energy. So let's understand how to develop the formula and expression for elastic potential energy. In this case, we'll discuss first for a body under longitudinal strain. So this is very similar to how we had discussed the concept of potential energy of a spring, half kx square, when it is under a compression or an extension, whichever be the case of x. So if we have a body whose natural shape is like this, but we have compressed or extended it, whichever be the case. So that equivalent type of formula we'll get over here for the body in terms of things like the extension. If this has become L plus delta x because of some external force, or it might have got compressed to L minus delta x or L minus delta L. So to take the body from its natural shape to a state of deformity, the work done by the external agent equals to the elastic potential energy stored. So work done by an external agent to deform a body from initial natural state that equals to the elastic potential energy stored in it. Okay. And you can also understand that this work done is basically work done against the internal restorative force. So this work done by external is actually work done by the external agent against the internal conservative force or the restorative force, okay, which is generated due to the elasticity of the material. Hence, it is called the elastic potential energy. Okay. Just make a note of this definition first, then we will see the formula for it. Okay. So you'll see just like in the case of the spring, the potential energy was proportional to x square. Here the potential energy will be proportional to delta L square, because delta L is the amount of deformity. But of course, it will also depend on the other properties of the body, like the Young's modulus, the area of cross section, the natural length, etc. Okay, so now let's see the derivation of the formula for this. So basically, let's say we are doing something like this. We have taken our particular body, which is longitudinal in shape, and we've attached it on one side to a wall or something like that. To begin with, it's at natural length, but now we start extending it from this. So at some point of time, it's extended to, let's say, L plus X under the action of external force, which will of course generate a tension, and there will be some kind of a reaction force at the connection point with the wall. Now in a small time dt, if we further extend it by dx, this is undergone a further small displacement of dx. So during that small displacement of dx, from here to here, the work done by the external agent is equal to F external into dx with a positive sign, you can see. So that is equal to the change in elastic potential energy, as per the definition that elastic potential energy is the total work done by the external agent. So it's like this. Okay. Now you can see that during this time, this is having a stress of T by A, is the area of cross section, Y is the Young's modulus. Okay, so that is equal to F external divided by E, because the tension is balanced by the external force. Okay. So it is having a strain X by L, okay, such that stress upon strain should be equal to Young's modulus. So F external divided by A upon X by L should be equal to Young's modulus. So F external at this point of time, when the extension is X, will be equal to this value. Okay. So to keep it stretched by a distance X, how much force we are applying? Ay by L into X. So now to further extend it by dx, how much work that force is doing? For that small displacement, it is doing a work of Ay by L into X dx. This is the work done for a small change in the extension from X to X plus dx. Okay. So now if our final state is where basically something like this happens, that it's got a final elongation of delta L. So going from our initial state, which is the natural state, to the final state, where the elongation is equal to delta L. Okay. So going from here to here, the total work done is equal to the elastic potential energy stored. That is the definition that we see. So according to this, the elastic potential energy is going to be integration of this. Okay. So as you can see, it is going to be integration of Ay by L into X dx for the limit that X is going from initial value 0 to final elongation of delta L. These are constants. So you will see that the formula we get for elastic potential energy will become 1 by 2 Ay by L into delta L squared. On substituting the limits, you get this. So as expected, our elastic potential energy is proportional to delta L square, but the constant of proportionality is half Ay by L. Okay. So we'll see that there is a connection between this equation and this equation also. So just go through this derivation quickly and note down the key points. Okay.
Sir, can you scroll up, sir?
Okay.
Please show the first slide.
Yeah, okay. So this is the definition of elastic potential energy and the concept of how we can calculate elastic potential energy as a work done by external agent against the internal conservative force or the restorative force in order to deform the body from some initial state where it was in natural shape to some deformed state. Okay, so done with this.
Yes, sir.
Yes,
Okay,
sir.
so now, yeah, so now come to the derivation part below. So we'll discuss a easy way to remember this final formula also, a shortcut method to remember the formula. But first of all, how the formula actually comes, it comes from execution of this derivation.
Sir,
It is actually L plus X plus dx. Now the dx is very small. Okay, so whether we change it or not hardly matters. Okay. At this point of time, the length is L plus X. Next moment is just increased by a small amount dx. So it's become L plus X plus dx. Okay. So because dx is very small, so during that change, we will take the strain as X by L only. So accordingly, the tension is this much only. It is AY by L into X, which is equal to the external force.
Sir,
Yes.
sir, this formula can be used for work done also. No?
Yeah, this is the work done by the external agent, and that is only equal to the energy stored in it. Stored in the. So you can just visualize this elastic material like a spring. No? So to stretch a spring, the work done by the external agent gets stored as potential energy. Got my point? No?
Yes, sir.
Okay. Okay, so now what we'll see is that there's an easy way to remember this formula by doing an analogy with a spring. Okay, so comparison of a longitudinal body under strain and a spring and an ideal spring, which we have learned about. In fact, ideal spring was also an application of Hooke's law that we had learned earlier. So you'll see that the working principle of both are the same. So we have this kind of a material. So whether we elongate it or we compress it, similarly, we have a spring, an ideal spring of natural length L. Now, whether we are placing it under a situation of elongation, okay, or we are compressing it, okay, so whether we are doing this by applying external force like this, which creates the internal tension in the spring, it's like this, or we apply the external force this way, so the internal restorative conservative force is like this. So similarly here, if we are elongating it under the action of external force like this, or we are compressing it under the action of external force, you'll see that here tension has a magnitude of kx. Okay, so F is equal to T equal to kx for both of these. Okay, whether we are talking about this diagram or this diagram, and the elastic potential energy of the spring is given by a formula half kx square. Here, whether we are in this state or this state, when we apply the formula, we have stress upon strain is equal to Young's modulus. So we get tension is Ay by L into delta L. And that is equal to the external force. So you can see that this formula is now comparable to this formula. Okay. And we just saw that the elastic potential energy stored is half Ay by L into delta L squared. Now you can see that the second formula is directly comparable to the second formula for our spring. So we can say that ultimately by comparison, what we can see here is that the longitudinal material which has elasticity, it behaves like an equivalent spring. Okay. So that means this behaves like an equivalent ideal spring. Okay, of K equal to Ay by L. Okay. And we are just replacing delta L with X. What we normally in the case of the spring, we denote the deformity of the spring by X. Now we are denoting it by delta L, and the property of AY by L, which you can see is a physical property for the given rod or the given material. It has a fixed value of area of cross section, it has a fixed value of natural length, and it has a constant value of Young's modulus, which is the material property. So AY by L is a constant for the given materials, given body. So it is playing the role of the equivalent spring constant. Okay. So just like by now you got used to this formula that the spring force is Kx and the elastic potential energy is half Kx square. So like that, the tension developed in such a material will be equivalent spring constant, which is Ay by L into the change in length, which is delta L. And the elastic potential energy will be half K into X square. So replace K with the equivalent spring constant Ay by L and the extension of the compression with the value of delta L. X, replace it with delta L. So that's a very easy way of solving numerical problems also, where there's a combination of materials, as well as directly relating these formulae with the more easy formulae of the ideal strings that we have seen before. So just make a note of this. This is very important.
Sir,
Yes.
sir, what is the value of K here?
K is a spring constant ना for an ideal spring.
Okay.
अंडरस्टूड ना? वो वर्क एनर्जी में याद है ना?
हाँ sir.
और न्यूटन्स लॉज में स्प्रिंग फोर्स इज kx, वर्क एनर्जी में potential energy is half kx square. It has the unit of Newton per meter, right?
Yes sir.
So now if you check dimensionally also, area into Young's modulus has the unit of newtons, because Young's modulus is in Newton per meter square. So area into Young's modulus divided by natural length is a physical quantity which has dimension of force per unit length or unit of Newton per meter, and plays the same role in the formula as the spring constant plays for an ideal springs formula, right? Okay, so hope you understood this point clearly. So we can see that this can be applied very effectively in certain types of questions. But before that, one more important point about the elastic potential energy. So from this formula of the elastic potential energy, you can also see that we can generate another formula for something called energy density. That is the potential energy per unit volume. In the deformed body. So that energy density, we can give a symbol of small e. So that is potential energy divided by the volume. So the volume is area of cross section into natural length. So that becomes half y by L square delta L square. When you divide this by this, so you can see that it is half of Young's modulus into delta L by L squared. Okay. So energy density we can express as half of Young's modulus into strain square. But keeping in mind that Young's modulus into strain is equal to stress. So we can generalize this formula that the energy density is half of stress into strain. So this becomes another important formula for us in the whole concept of elastic potential energy in a deformed body. That per unit volume, the energy stored or the energy density is half the product of stress into strain. Okay, now an important type of example.
Sir,
Yeah.
sir, 1 minute, sir. Please
Okay.
scroll. Yes, sir. Done.
Okay. Now suppose next we have this kind of situation that, at the corner of a wall and a floor like this, we have just kept two elastic longitudinal materials against each other. So you can even think of them like longitudinal blocks kind of things that we have kept. So this one is the body A. And against that we have kept another body. So like this one. So A has a natural length of 5 meters. It's made of Young's modulus. The material has Young's modulus of let's say 2.5 into 10 raised by 11 Newton per meter square. And the area of cross section that it has is, let us say, 6 centimeters square. Whereas B has a natural length of, let us say, 3 meters. The Young's modulus of the material is 6 into 10 raised by 11 Newton per meter square. And the area of cross section of the rod B is, let us say, 4 centimeters square. Okay. So these are metallic rods or planks. A and B. Now what we want to do is we want to apply some force at this end, okay, of this combination, so that what happens is that as a result of this whole combination gets deformed. So next what we want to do is we want to create a situation where something like this is going to happen, that so this whole shape will be under deformity as a result of this, because of some external force that I'm applying. So some amount of external force is going to cause the right side end of the block B to get displaced inwards by this much. So given all this, we have to find out if the right end of B is pushed by an external force. Okay, to displace it by S equal to 2.4 centimeters. Okay. Then we want to find, first of all, the force in newtons. Okay. Then the individual compressions for each of the rods. And the stress and strain in each rod. And also the elastic potential energy stored in each of these. Okay, so this type of question you will see, it's very helpful to entirely visualize the whole problem as instead of two materials which have elasticity, just think of them like two ideal springs which are kept against each other, back to back. So it's like a series combination of springs. So how we could apply the simple mechanics concepts for a series combination of springs that we can apply over here.
So can you scroll up for a minute? I missed a sentence on the last.
Okay.
Thank you, sir.
Okay, so anyway, let's see. This should be fairly simple. So what you have to do is you have to think of, this is like equivalent of two springs which are attached to each other like this. Okay. So if this combination of springs is under the action of this external force, okay, so each of them will be in some kind of compression. Okay, so now in equilibrium, you can see that the tension should be same in both of them because the net force at the junction point should be zero. Okay, so therefore tension in the first spring, you can think of this like having spring constant Ka, this has spring constant Kb. So tension in the first spring must be equal to tension in the second spring, which must be equal to the external force that we apply. Okay, so T is equal to F. Okay, now T is Kaxa is equal to Kbxp. Okay, where this is having a compression of Xa from its natural shape. This is having a compression of Xb from its natural shape. Okay, which in this diagram you can see is that this is like this. So if you also compare this with the earlier diagram, you can see that Xa plus Xb, or basically delta La plus delta Lb, is that displacement S. Now when we convert this to equivalent spring, we can see that it has an equivalent spring constant, which is Ay by L. So its equivalent spring constant from here is equal to this much. It is 3 into 10 raised power 7 Newton per meter. Okay. So this rod will act like an equivalent spring of this much constant. Similarly, B will have an equivalent spring constant of area into Young's modulus divided by length. So this is acting like a spring length. Okay. So now you can see that we got the value of Ka, Kb. They are 3 into 10 raised power 7 and 8 into 10 raised power 7. So from this you have the ratio of Xa's to Xb is the ratio of the inverse ratio of the spring constants. So eight is to 3, and Xa plus Xb is equal to S, which was given to us as 2.4 centimeters. So that means Xa will be 8 by 11 times S. And Xb will be 3 by 11 S. So from this now we know that the individual compressions will be this much. And then from that we'll find out the tension, and from that we'll find out the amount of force also. Okay, so these are the individual compressions. Now about calculation of that external force. So tension is equal to KAXA is equal to KBXB. That is equal to the external force. Okay. So whether we take Ka, which was 3 into 10 raised power 7, and multiplied with Xa, only this will be in 10 raised power minus 2, because this is in Newton per meter, this is in meter now.
Okay.
So this is a kind of external force we'll have to apply. This kind of external force will create that displacement of that point of application of force by 2.4 centimeters, which will create the individual compressions of delta LA and delta LB, and further the individual potential energies and all that. So rest of the things all will come from formula. So we have converted the above system into a system of equivalent springs, and from that we have understood. So basically this system here is converted to equivalent spring system. Okay, so now once we've got this force, so now you can see that for example, the second part, the stress in each rod, it is equal to T divided by this area of cross section. So it's force divided by that area of cross section. The stress in the second one will be the same tension divided by its area of cross section. And then from that, the strain okay, so we got these lengths delta L's over here. We'll just substitute these values. Okay. And now the last part, the potential energy is stored in each one. So you already know that this term is so this will give us the potential energy in joules. Okay, like that for the second one. So on and so forth. Okay. Okay, so this was sort of an example where we converted the combination of materials under longitudinal stress into a series combination of springs. Now, next example, let's look at something where it's equivalent to a parallel combination of springs. Okay. And that's generally going to be easier to do the calculation. so we have sort of a block made of cement on a smooth floor, and now A and B are metallic blocks but longitudinal in shape. So both have a natural length equal to 2 meters, but A and made of materials of Young's modulus. Like this. Now we want to apply a force like this on this block so that the cement block gets pushed through a certain distance. You have to calculate that force. So through a displacement of, let's say, 3 millimeters. This is a rigid wall. So find the force required in newtons and so the stress and strain in A and B respectively, that's going to be a little bit tricky. So we'll discuss that in detail. But first of all, it's quite easy to calculate this net force. Just try to work this out. Yeah, I'll scroll up.
Sir, sir,
Yeah,
sir, please scroll down.
scroll down. Okay, finished. Okay. Okay, so as you can see, this will become a very simple application question. So you can treat this like a combination of two springs. So whatever force we are applying from this side, it will be the combination of tensions, let's say TA and TB in each one. So you can see that X for spring A is equal to X for spring B is equal to this displacement, okay, is equal to 3 millimeters. So TA will be equal to KA into X. F will be equal to TA plus TB. And stress in spring A will be whereas strain for both of them will be same. That will be this displacement divided by the natural length. Okay. So now let's calculate the equivalent spring constants. So area into Young's modulus divided by natural length using this formula. So same. So each of them will have a tension of 900,000 newtons. So the net tension will become net force on this. Okay. And accordingly, you can calculate the stress in each. With the strain. Okay, so as you can see, this type of situation becomes very easy. Each of the equivalent springs is exactly in the same state. They are compressed by X from the natural length. So basically, delta LA is equal to delta LB is equal to this X, whereas natural length of A was equal to natural length of B, was equal to the L. Okay. Okay, so with this we complete today's session, people. Next session we will wind up elasticity, and we'll move into properties of fluids, that is surface tension and viscosity. And on completion of this, we will spend some time with the doubts of properties of matter and any pending doubts from hydrodynamics from before. We will complete at that stage. Though all this is quite formula based, as you can see, so these are not very difficult chapters. You can complete them quite fast. Continue working out questions from HC Verma as well as from your module, and we'll discuss doubts as we come to the end of the topic. Okay? So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Bye, sir. Thank you.
Okay, bye, people. Have a nice day.